My name is Today I will present final project control system for robotics. I choose the system question car suspension model. Conventional passive suspension model use a spring and damper between the car body and wheel assembly. The spring damper characteristics are select to comprise one of several conflicting objectives such as passenger comfort, load handling, and suspension deflection. Active suspension allow the designer to balance this objective using a feedback controller, hydraulic actuator between the chassis and wheel assembly. The question car model of the active suspension system, the mass MB represents the car chassis, and the mass MW represents the wheel assembly. The spring KS and damper BS represent the passive spring and shock absorber placed between the car body and the wheel assembly. The spring KT model, the compatibility of the pneumatic type. The variable XBI, W, XWI, and R are the body travel, wheel travel, and load disturbance. Repetitively, the force Fs applied between the body and wheel assembly is controlled by feedback and represents the active component of the suspension system. This is the system, and this is the space equation for the vector car model. This is the design setup. Okay, and course MATLAB. Find the frequency domain, set domain, and time domain. Okay, go to MATLAB. This is code of system. Run. The system will have 10 graphs. Graph 1 show the gain form load, this and actuator force to body axle and suspension travel. Because of the imaginary acid zeros, feedback control cannot improve the response from load disturbance or to body acceleration at the time of frequency, and from R to suspension deflection is at the retrospace frequency. Graph 2. Graph 2 is show the result is an uncertain state space model of the actuator plot the board response of 20 sample volume of it and compare with the nominal volume. And graph D show the response to load disturbance. Specify code loop target for the gain form load determined are to suspension, deflection, and body acceleration because of the actuator accidentally and imaginarily acid zero only seek to external disturbance before below 10 radius per second. And graph 4. Graph 4 show the body travel suspension, deflection, and body acceleration due to load. And graph 4. Graph 4, graph 5. Graph 5 show the time domain evaluation. Observe that the body acceleration is smallest for the controller, emphasizing passenger comfort, and largest for the controller, emphasizing suspension, deflection. The balance design achieves a good compromise between body acceleration and suspension deflection. And graph 6. Graph 6 show the simulate the nominal response to a load bump with the robust controller curve. The response are similar to those obtained with the balance controller. And the next simulation. And the next simulate the response to a load bump for 100 actuator model randomly select from the ascertained model set 8. And graph 8 show the robust balance design. The robust controller curve reduce variability due to model uncertainty and deliver more consistent performance. And graph 9. It shows the robust performance margin as a function of controller order. You can use the simulate controller order for with the robust performance is above 1. And the last graph show the turn controller has performance RP equal to 0.92, very close to that of Go. You can see the board the funding using. And that's all. And this is the result. Q click equal to 1 multiply 1 T multiply 1 array of ascertain continuous time state space model, and S model has 5 output, 4 input, and 9 states, and the following ascertain box. And decay interaction summary best achieve robust performance equal to 0.90806, sorry, and decay interaction summary best achieve robust performance equal to 0.916. Okay. That's all for my present. Thank you.